Hi there. This video is just going to walk through a couple of applications of the isobaric thermal expansivity coefficient and isothermal compressibility. We introduced these two factors or coefficients when we started talking about enthalpies of reaction, and they are particularly helpful in terms of helping us to predict the behavior of certain substances when we change the temperature or we change the pressure. So alpha P is going to be relevant when we're changing the temperature at a constant pressure, and then our kappa T will be relevant when we're changing the pressure with a constant temperature. One thing that is nice is if we factor in only relatively small changes in temperature or pressure, we can use these simplified variations of these equations to do some simple calculations. So we'll take a look at those in a minute, but first let's just take a look at exactly what these equations are telling us. So our first question is asking us to describe the isobaric thermal expansivity coefficient, or equation 1 from the previous slide, in your own words. So take a minute and see if you can write down, just using words, what you think the first equation that we have identified here is. So try to describe this mathematical expression in your own words. Okay, so hopefully you have taken a minute to see if you can put into words what this equation is telling you. So looking at this, what I can see is that this equation is saying something about how the volume of our substance changes as we change the temperature at constant pressure. Okay, so really just trying to get at, can you determine what an equation is helping you to figure out about your particular situation. So essentially what we're going for is some description along the lines of a fractional change in volume that accompanies a rise in temperature. Okay, is generally how we're going to utilize the alpha P coefficient. Now, the other part of our question is asking us what it means for a substance to have a large value of alpha P. Okay, so just looking at our equation, we can see that if we have a large value of alpha P, that means that our substance must have a pretty strong response to a change in temperature. Okay, so a large alpha P means we're going to have a large change in volume with a rise in temperature. Okay, so we've summarized now what this expression, what kind of information this expression provides for us. The one last thing I'll point out here for our alpha P is that notice that we have this term out front, this 1 over V. Okay, so since we have our volume in the denominator here, what that's telling us is that this expansivity coefficient is also dependent on the relative volume of the substance that we're considering. So larger volumes are going to, in turn, factor into a smaller response overall for the substance with temperature. Okay, so if you're thinking about very large volumes of water or volumes of another substance, that relative change in volume with the change in temperature is not going to be as significant as if you have a smaller sample size. Okay, so let's put this expansivity coefficient into practice with a simple example. So using a real-life example to work with, let's consider climate models. Okay, so those climate models, a lot of them predict that Earth will warm between 2 and 6 degrees in the next century if we keep with our business as usual practices. So what we want to do here is to use our new skill, our new tool of our expansivity coefficient to calculate the rise in sea level associated with the minimum anticipated temperature increase. So we'll calculate it for just a 2 degree Celsius increase. So we have some information here to help us out. So we've been given alpha P for water of 2.1 times 10 to the minus 4 per Kelvin. So you can go back and look at that expression for alpha P and satisfy yourself that your units should come out to a inverse temperature. And then we'll also assume that the average depth of the Earth's ocean that's affected by warming is about 1,000 meters. Okay, so realistically, the entire depth of the ocean is not going to be affected by increases in atmospheric temperatures. Okay, so it's really just that first 1,000 meters that gets affected. Okay, so again, this is a perfect example of where we can use that simplified expression. So our relative change in temperature here is pretty small, so 2 degrees is not a lot in terms of a change in temperature. So let's use our expression that we were given on the first slide, where we know that the change in volume over V is approximately equal to alpha P delta T. All right, so now at this point, it's really just kind of a plug and chug problem. So we'll put in our alpha P value that we've been given. Don't forget to put your units in there. Okay, and then we want our delta T. In this case, we're going for that minimum anticipated temperature increase, which is 2 degrees Celsius. And just remember that temperature changes in Celsius and Kelvin are going to be the same as long as you're working with delta T's. So we can keep that as 2, and we'll just put our units of Kelvin there to match up. And when you calculate that, you should get a value of 4.2 times 10 to the minus 4. Don't even need a calculator for that one. And then that comes out to about, if we want to put it in a percent format, 0.042% increase in volume with a 2 degree change in temperature. Okay, so looking at this number that we just obtained, 0.042% increase in sea level rise, that probably looks like a super tiny number that can't possibly be significant on a global scale. Okay, well, let's see exactly how significant that number is. So let's take into account the depth of water that is affected by this warming. So we'll calculate the actual magnitude of sea level rise for that quantity of water. So we'll just take our value that we've calculated up here and multiply it by our depth that's affected. So here we will have 1,000 meters times 4.2 times 10 to the minus 4. Okay, that comes out to be 0.42 meters, also known as 42 centimeters, also known as about 1.4 feet, if you like your American units. Okay, so stop and think about this number right here. So if our sea level rises by 1.4 feet, okay, think about if you are living in an area that is at sea level or even below sea level. So areas like Miami, okay, that is a catastrophic amount of sea level rise. Okay, that will be just devastating to a lot of communities that are at sea level or below. Okay, so just that 2 degree increase in temperature, okay, really can have very significant, very impactful consequences for people. All right, so moving on to our other equation of interest here. So looking at the isothermal compressibility, let's see if you can take a minute and try to describe this equation in your own words. So looking at this expression, what is this telling you, or what kind of information would this expression help you to obtain? So take a second, jot something down, and then I'll be back to give you some hints. Okay, so hopefully you took a stab at describing what this equation is telling you, but looking at our expression, we can see that this is saying something about how our volume will change with changes in pressure when we're at a constant temperature. Okay, so kind of a similar idea to what we talked about with the alpha P, or expansivity coefficient, but here we're looking at changes in pressure instead of changes in temperature and how that affects the volume of a substance. All right, the other thing that we want to think about here is what does it mean for a substance to have a large value of kappa T? Okay, well, in that case, a large kappa T is just saying that we have a sample where the volume will decrease significantly with pressure. Okay, so remember we have a negative sign here. Okay, so essentially that negative sign is ensuring that we have a decrease in volume with an increase in pressure. Okay, so this is a summary of what the kappa T, or the isothermal compressibility coefficient, describes for us. And again, just remember that negative sign that we have included here really is just there to ensure that kappa T is a positive quantity, okay, and that fits with the idea that as we increase our pressure, we're going to decrease the volume of our substance. All right, let's do an example to put this into practice. Okay, so here's a typical application of our isothermal compressibility factor. Okay, so we have some information here that tells us the deepest part of the ocean has a depth of about 11,000 meters, and we want to know what the relative volume change is at that depth. Okay, so we're given some information that will be useful. So we have a value here of kappa T of our compressibility factor of 5.5 times 10, of 5 times 10 to the minus 5 per bar. All right, and then we're going to also assume that kappa T is approximately constant for solids and liquids. Okay, so that assumption is valid because for our condensed phases, solids and liquids, those relative volumes aren't going to change a whole lot with compression relatively between your solid and liquid phase in comparison to picture if you have a gas, right? Gases are very compressible. That volume change is going to be very significant with pressure. So solids and liquids will stay approximately constant. Gases are not going to fall into that assumption. So just keep that in the back of your mind when you're working with these types of problems. All right, so let's dive in. So remember from slide 1 that for relatively small changes, right, we can use this simplified expression for our change in volume. Relative change in volume. So delta V over V is going to be represented by our compressibility factor multiplied by the change in pressure. Okay, so the information that we need is our delta P. Okay, so we've been given our kappa T in our problem. The only other thing that we need to get our relative change in volume is the information about the change in pressure for that depth of water. Okay, so let's sketch a little picture about what we're talking about. Sometimes that helps to get us thinking about where we want to go. So we have a situation where we have a depth of water that we're thinking about. So we have our surface water, and then we're going to go down to a depth of about 11,000 meters. Okay, so hopefully when you start thinking about a picture like this, it's screaming, and about pressure, it's screaming to you that you need to think about that hydrostatic pressure that we've encountered before. Okay, so that's that rho GH that we have to factor in when we have a depth or a column of water that we're working with. Okay, so we know that at the surface, that's just our normal atmospheric pressure. So let's say that P is 1 bar up here, and then we need to know what P is at our 11,000 meter depth. So we know that that's just going to be our 1 bar surface pressure plus our hydrostatic pressure, rho GH. Okay, so just a quick run through of how to calculate that hydrostatic pressure, the rho GH part. So key here is to remember your units, all right? So remember density, 1,000 kilograms per meter cubed. G is 9.8 meters per second squared, and our height here is 11,000 meters. When you use those units, you get a unit of pressure of pascals. We are working with bar, so we're going to do one more conversion there and end up with about 1,100 bar as our pressure down here. Okay. All right, so now we are ready to plug everything into our expression. So remember, we are looking for our relative change in volume here. So we're going to plug in our kappa T, 5 times 10 to the minus 5 per bar, times our delta P. So we've got P final of 1,100 bar minus 1 bar is still about 1,100 bar as far as our precision is concerned. So plug that in there. So then we end up with a relative volume change of minus 0.06. Okay, so that's about a 6% decrease in our volume. Oh, and I just realized that in order to get that negative sign to come out, we actually need to remember to put our negative sign in our expression. So there's a negative in front of that kappa T. All right, so and put a negative there. Okay, now everything's happy. So that is how you would calculate the relative decrease in volume that's associated with a change in pressure. Okay, so our 11,000 meters of ocean water compress that water by about 6%. Okay, so the water at the bottom of our ocean is about 6% denser due to compression. Okay, so why is that significant? Well, for most of us, it's not. Not many of us are going to be going down to depths of 11,000 meters, but if you are a scuba diver, that compressibility due to mass of water on top of you is important, and also if you are a scientist that does research on things like hydrothermal vents or other things that are at the depths of the ocean, those are things that you need to take into account when you are developing your little remote submersible rovers that you drive around in, and all kinds of fun stuff like that. So hopefully you found that to be a helpful exercise. So just walking through some applications of these to ways that we can think about changes in volume, again, with respect to temperature or respect to pressure. All right, hope that helps, and we'll see you next time.